So we're here today because we want to learn a lot about Java. My name is Sander Mak. I'm part of the Picnic Tech Leadership Team. And what a morning it has been for Picnic, right? With the award and everything. However, I am not going to talk about the automated warehouse. There will be a talk in the afternoon by Sjoerd and Matthijs, who were on stage. So if you want to know more details about this project and about the cool stuff that is happening there, highly recommend going there. However, this talk will be about a tool that has enabled this team to actually do the work that they did. So also very interesting, I would say. And I'm actually going to let you in on a little dirty secret. Because we, as conference speakers, we really like to talk about new, cool technologies, new frameworks, new languages, new everything, right? And that's cool, and people seem to like that kind of talk. But in the end, what do you really take away? What can you actually use in your day-to-day? And I think there's place for these talks, but there's also place for more practical talks. And this is actually going to be a very practical talk. Because in this talk, I'm going to teach you a superpower. And this is a superpower that you can take away today and take to your team tomorrow already. This is something that you can apply to any Java project that you're working on. And the superpower that I'm talking about is to be able to refactor at scale. So I hope I won't have to convince you of the advantages and the benefits of refactoring, right? So I'm not going to do that. Let's just say that a lot of code bases would really benefit from having some refactoring time to time. And I'm not talking here about everything that we learn to do in IntelliJ. So refactoring at scale doesn't mean learning all the shortcuts and everyone doing this frantically in their IDEs. No, when I talk about refactoring at scale, I really mean something that you can work into your CI pipeline, that you can work into your automated processes that can help you scale the process of refactoring your code and making your code better. And the tool to do this, and the tool that we use at Picnic, is called ErrorProne. This is an open source project created by Google. They also use this heavily internally, and they published this quite a few years ago already. And I think it's a really, really cool tool. It is also not that well known in the Java community, and that's a pity, because I think it can bring a lot of value to a lot of projects. So that's also why I'm here, sharing how we at Picnic use ErrorProne to improve our code base, to improve our way of working. Now, before we dive into the details of ErrorProne, I would like to sketch a little bit of a picture of what it is that we try to achieve at Picnic and why we actually care about having such a tool at our disposal. So, this is what I call the online groceries challenge, right? So what we want to do is we want to make grocery shopping, online grocery shopping, fun, easy, and affordable for everyone. So the idea basically is pretty simple, right? We have an app, people can order there, then you can select a slot, and the slot is pretty precise, so people are happy that they don't have to sit at home for the whole day. We make sure that all the groceries are picked and delivered at the right time to your doorstep, no delivery fee. And we have to make sure, as a tech team, that this actually works. And that's a pretty big challenge, because being able to fulfill this many orders, being able to actually ensure that our electric vehicles are at the right place at the right time, that takes a lot of software. And people are really happy when they open what we call our delivery radar, where you can see the electric vehicle coming to you, delivering your groceries, so that you know exactly where it is. This takes a lot of tech. I think you can see that. So yes, we built the obvious backend, and we have the obvious app, of course, that we built. But there's so much more behind the scenes. We need to make sure that in our warehouses, every order picker is working efficiently. We need to send our drivers out into the world and navigate them to where they need to be. Make sure that they deliver the right groceries at the right place. Lots of apps, lots of systems that are going on behind the scenes. So to give you a bit of an overview of the numbers that are currently at Picnic, the company is 6 years old, and it has grown from a handful of engineers who built the prototype and made sure that we could do our first delivery, to a team of 180 engineers at the moment, and doing many, many, many more deliveries weekly, as we already heard in the automated warehouse project this morning. Only from there, we will already do 150,000 deliveries every week. So these are really, really huge numbers. And also looking at the code bases that we have, of course, we started out with some off-the-shelf software, but we are starting to develop more and more systems of our own as we scale, because a lot of the off-the-shelf solutions just don't fit and don't work at our scale anymore. So these 4 million lines of code, I mean, these have been built up over the past 6 years. A team of 180 engineers. This takes a lot of automation to actually guide this sort of way of working into something that is a quality code base and that is workable for a longer time. Now, some tools that are pretty well known do help in improving your code base, right? For example, SonarQube, already mentioned this morning. It's a tool that we use as well, and it's pretty decent at what it does. But at the same time, I do very much recognize the remark that Michelle had about broken windows, as you see. Because, I mean, you can see you have like 10 days, 20 days, 30 days of technical debt. What does it actually mean, right? Are people actually looking at these results? And if they do, is it really embedded in your development cycle? So you end up in a situation where you can see some trends, but you're not really in control in making your code base really, really better. Now, it is good to know your code, it's good to see trends, so I'm not bashing on SonarQube in any sense, but it's just not enough at this scale to ensure that you are doing the right thing at scale. So we want more automated sanity in our process. Now, there are other tools which are also fairly well known, I would say, things like Spotbugs and Checkstyle, all kinds of Maven plugins and tools that you can use to actually prevent things from getting worse. And these really do tie into your development cycle, into your build tool, so that is also giving you more feedback. But what if we could take it a step further, and if it's not just a tool yelling at you that you're doing it wrong, but a tool that actually fixes things for you and that helps you encode patterns and best practices and helps you do refactoring at scale. Now, error-prone is such a tool, and Refaster, another project that's very closely related, we'll also discuss, is also very important in this whole setup. So what is error-prone? Basically, error-prone itself is a Java compiler plugin. Can a Java compiler have plugins? Yeah, actually it does. It does have the capability of loading plugins. Not that often used, but for this use case, it fits pretty well. Now, error-prone itself, as a plugin, can analyze your code and can look at patterns and can actually already spot a lot of predefined bug patterns that are inside of error-prone itself. So that capability is a little bit like Spotbugs and PMD and things like that that already offer this kind of capability. By the way, there's over 500 of these predefined checks. They're all well vetted and well maintained. There's a good description of everything that it checks and does for you. What is also important is that the error-prone compiler plugin supports both Java 8, 11, and 17. And the last one is also pretty important for us because 2 weeks ago we migrated most of our services to Java 17, which is a completely different talk for a different time, but also very cool, I would say. But anyway, this tool does support it, and that was key for us to be able to migrate and to use error-prone. And if you go to the error-prone side, there's a very cool testimonial by Doug Lee, the guy who created the Java util concurrent libraries, where he says, well, it's a bit embarrassing. I guess I'm back to liking error-prone again because it found a bug in one of the Java util concurrent libraries. Though it annoys me sometimes. Well, I think that's a sentiment that we can all recognize, right? If we don't like to be pointed out errors, but in the end, it's all for the better. Now, I can talk a lot about error-prone, but how about we just look at some code, right? So I'm going to switch into my IDE, where we have a very, very simple Java application called My Buggy App. There's a bit of code here. We print something, we check some arguments, then there's an exception, and then we print something again. There's even some empty method, which we'll look at later. But who sees the problem here? Will this compile, by the way? Yeah, exactly. There's new illegal argument exception, but we're not throwing it. Now, if we just compile this code, right, so maven clean verify, there we go, then we will see it compiles fine, right? So it's syntactically valid, but it's most likely not what we meant and what we want. So what we can do with error-prone is we can go into our pom.xml. We can go to the compiler configuration, because remember, error-prone is a compiler plugin. And we can insert the configuration for error-prone, where we introduce the annotation processor path here, and we point it to com Google error-prone and error-prone core as an artifact. And just by doing this, we can run Maven, well, let's just say Maven verify again. There we go. Let's clean it as well. And what we see happening now is that we are actually getting a compiler error. And this was not there before we added error prone to the annotation processor path. And this compilation failure says, hey, you created an exception, but it's not thrown. And this is most likely wrong. And the cool thing here is there's a link to the bug pattern, so you can read more about it if you want to, if you don't really understand what is going on. You can click on it because it's just a compiler error, so IntelliJ knows where to point you. But what is also really, really interesting is that it doesn't just tell you about the type of error. It also has a real suggestion here, which is completely context aware. So it says, did you actually mean throw new legal argument exception? Why? Yeah, indeed, that is what we meant here. So this sort of supercharges the Java compiler with a lot of additional checks that you already get out of the box with error prone. Now, the nice thing about this being a compiler plugin is that it's really build tool agnostic, right? So you can configure a compiler plugin in any build tool. So it's not really a Maven plugin or a Gradle plugin or anything like that. It's really core to the Java compiler. But what we can do as a next step with error prone is take it up a notch, because yeah, we have a great suggestion here, but the next thought that you might have is, wow, if this suggestion is already there, can it also be applied for us? And the interesting thing is that the answer there is yes. Because if we go to this configuration here, we see that we actually configure error prone as a plugin to the compiler. We also have to set the compile policy to simple, because the error prone compiler plugin does have some assumptions about the way the JDK compiles, which are only satisfied if you set this policy. There's a JDK bug open to make this actually make it work with the defaults as well, but that's unfortunately not resolved yet. But anyway, we can configure error prone itself as well. So in this case, we can add some additional arguments to the error prone configuration, where we say, we don't want to do checking, but we want to do code patching based on these checks. And now this EP patch checks, there we have to list which checks we actually want to apply. So in this case, it's the dead exception one. You can see that is also the identifier that is used here. And we're going to say the patch location to apply the patch is actually in place. So this is a special token. You can also specify another location, and then it will just emit a diff, a patch file that you can apply yourself with some tooling later. But for this demo, let's just do in-place patching. And if we now say maven clean verify, you see there's no error, right? So, because we don't do checking, but we're doing patching. And that has actually fixed our code. So it says now, throw new legal argument exception. And I think that's really cool, right? So we have a tool that knows about some patterns, and it doesn't just warn us about it, it doesn't just give an error, but it's also capable of actually fixing it for us. And I think that is really, really powerful. So let's get back to what we were talking about in terms of error prone. So what do we have here? We don't have just a tool that is capable of telling us that we're wrong, but it's actually sort of like autocorrect, but for code. And I think a lot more useful than a lot of the autocorrect scenarios that we're familiar with. The nice thing is, this seems a fairly trivial one, right, the dead exception. But it is not just core Java that is addressed by error prone. So there are a lot of patterns that are indeed about core Java APIs and core Java usage. But there's also a lot of predefined patterns and checks already that work, for example, very well with Android codebases, or with codebases that use the JUnit library, where there's also, of course, some best practices and some anti-patterns, or things like the Joda library. So all of these are already bundled into error prone itself. Now, if you are using error prone, then you might, if you run it on your code base, run into some errors or warnings that you might disagree with, right? That happens. We all have sort of differing opinions. I feel very confident that the set is pretty well defined and pretty complete. But if you want to, you can also, in the configuration of error-prone, override what it actually does. So you can tone down a compiler error. If a check results by default in an error, you can tone it down, for example, to a warning by saying -xep, and then colon the name of the check, and then providing the level, the severity that you want to assign to it. It might also be that you just want to plainly skip some of the checks. For example, in our code bases, we build backend services, so we just disable the Android checks. These are not really relevant to us, so why waste CPU cycles actually doing that check? Now, there's also cases where, in general, you might want to have the check and want to apply it to your whole code base, but there are some tiny exceptions in your code base where you want to allow this sort of anti-pattern or this bug pattern to occur. Or you want to do this because you intend to clean it up later. In that case, you can use the standard suppress warnings annotation that Java has, that you can also use to suppress Java's own compiler errors. You can use the same mechanism to also suppress these error-prone checks and these bug patterns that are in there. So that's all quite flexible and really tunable to your own taste, let's say. But again, I think already by default, the stock configuration that error-prone comes with should be a very good guideline for most code bases. And it's a really well curated set of bug patterns and checks that are in there. I want to highlight one other check that error-prone does that I feel is very valuable, that we also use within Picnic. And that is the var check rule that is in there. Now, you all might have this annoying coworker probably in your teams who says, we should be fully immutable, right? And I think there's a lot of value in there. But as soon as you start pushing it to the max and say, okay, well, then everything needs to be final, and then we need to put final on everything, then it starts to get annoying, right? Because it's also visual noise in your code. And yes, you sort of know the value of it, but do we really want to make our code uglier just to get this? And it doesn't have to be this way. With the var checker and the var check that is in error-prone, you can actually invert the default. So if you enable this check, then by default, everything is assumed to be final in your Java code. So the local variables, the parameters, anything where Java has the assumption that it's non-final, now the assumption is flipped around and you say, okay, it's final. However, if you still want to have a mutable variable, you can by using this add var annotation, which comes from error-prone. And there you may reassign and may use it as a mutable variable. And I think it's a really cool thing because in the end, yes, we do want to encourage immutability in our code and we do want to encourage people to think in that way, but we don't want the visual noise of final everywhere. So by flipping this around and by having error-prone check this for us, that's a really powerful tool to have a cleaner and also more, let's say, reliable code base where you can more easily reason about immutability inside of your code. So that's an example of something that's not really a bug pattern or something, really trying to find problems in your code, but where you can actually flip some of the Java defaults around in the compiler and then have error-prone enforce immutability for you for these local variables. So we've seen that with stock error-prone, you get a lot. You can configure it pretty well. But the nice thing is there's also third-party contributions, third-party checks that you can work into error-prone. There's, for example, the Mockito team has also released error-prone checks that you can add if you are using Mockito for mocking in your code. And there's a contribution also for SLF4J. So if you're using the SLF4J API, there's some do's and don'ts in there that can be enforced much more easily if you do this. But that sort of raises the question, right? Because wait a second, if people can actually publish this to Maven Central, then it does mean that you can create your own checks, right? And your own way of working with error-prone. And that is indeed actually the case. And that's what I want to show in a second demonstration. So what we're going to look at here is I'm going to introduce another Maven project, which is called my BugChecker plugin. And here we're going to build a very simple BugChecker implementation that error-prone then uses to apply it to your code base and to automate this check and maybe even automate this rewriting that we were talking about. So this is a different Maven module that we're going to create. And the core of it is a class where we're going to extend the BugChecker type. That is an error-prone type. Now, once we have that, and we have compiled the jar file for my BugChecker plugin, we can add it to the annotation processor path of our buggy app application and actually start using that BugChecker. And error-prone uses a mechanism called service loading to actually find implementations of these BugChecker types in jars that are added to the annotation processor path. And we'll see that we can do this pretty easily using another Google library without having to dive into all the details of this service loader mechanism, where usually you would have to create in the meta-inf directory a certain named file pointing to the implementation class. We don't have to do all that because there's better solutions for that as well. So let's head to the IDE again. And in this case, I'm in a second project called my BugChecker plugin. We can see here on the POM configuration that we are just invoking the Maven compiler plugin. We're not running error-prone here because we don't want to go full inception. But we are just configuring another annotation processor, which is called Google Autoservice, which allows us to just put an annotation on a class, and it will be service loadable by other implementations like error-prone. And furthermore, there's a few dependencies because, well, we're going to write against error-prone APIs here, so these are also listed here in the POM. So let's look at the code. I already have a little bit of a stub here where we say what we want to do is create a BugCheck rule that checks for empty methods because, well, why would you want an empty method, right? We don't really want that. And we have one right here in our buggy app. So that's the goal. That's the one that we want to flag. So we extend BugChecker, which is an error-prone type, and we implement BugChecker.method tree matcher. Because what a BugChecker effectively does, it allows you to walk over the AST, the abstract syntax tree, of your Java code, the code that you're checking. And it uses a kind of a visitor pattern, or actually it uses the visitor pattern. And here we are interested in actually only visiting method declarations. So we can do that by overriding the match method implementation, and then we get a method tree, which is a sort of the subset of the AST that represents the method that you're currently inspecting. But before we go there, we need to ensure that we actually say that this is an auto service for the service loading, as I said. So we need to define BugChecker.class as the actual type under which it will be loaded. And there's an annotation called bug pattern that contains the metadata of the pattern that we're creating. So we need to give it a name. Let's call it empty method. There we go. We need to give it a summary. Yeah, so we don't like do nothings. There we go. And we also need to assign it as a severity. And in this case, we're just going to say, let's make it an error, right? Because why not? And now, there's of course the meat. How are we going to implement this check? So of course, I picked an example which is pretty straightforward to implement. So in this case, we will look at the method tree. We say, give us the body of the method, and give us the statements of the method, and let's see if it is empty. And if it is empty, we are going to return a description of a match that we've made here. And we actually matched this method tree that we just inspected. And we're going to give it a suggested fix. And the suggested fix here is to delete this method tree. So this is basically setting up our check so that it can find the right method, and it can also say as a suggestion that you probably mean to delete this. And it could mean that you delete multiple lines in the source code, right? Because the method is opened and then curly brace and then enter, curly brace close, or it could be a one line. So this is not about source line codes, but this is about nodes in the abstract syntax tree that we want to flag. And the compiler infrastructure itself will turn this into source lines and will make it work as if by magic. Now, here we are going to return a description no match, because, well, if the method wasn't empty, then apparently our check doesn't match. And I mean, we can make this much more complex, right? We can check maybe if it's a method that's annotated with override, because we have to override it and we just leave it empty, then we might make an exception. So you can make lots and lots of tweaks to the rule, but let's keep it simple for now, and let's do it like this. Now, what I'm going to do is I'm going to Maven clean install this one, so we want to put it into our local repository as a jar file. There we go. And what I'm also going to do is I'm going to copy the coordinates of this jar, or this Maven artifact now. And I'm going to go back to my buggy app, and we want to apply the rule here. So let's go to the POM file, and in the annotation processor path, we're going to add this new jar file that we just created. Let's paste it in. Now we also need to enable it, right? So we're going to add empty method, which is the BugCheck that we just created. And now what we would expect is, well, looking at the code here, is that the method that is here, that it will be removed, right? Because we had the suggested fix. We are going to match this method because it's an empty one. So let's see Maven clean verify what is going to happen here. And poof, it's reloaded, it's gone. Right. So we created, wow, yeah, it's magic, right? Woo. So what we did is we created a fairly easy bug pattern that matches in your AppSec syntax tree and then has a suggested fix. Now, just to make the picture complete, let's undo this, and let's try to run the same check, but not as a patch, but just as an error-prone check, which is the default mode. So we're going to remove this patching code, and we're going to actually have a look at what happens if we now run the code with this empty method in place. And we'll see that we are getting a compiler error. And this is one that we defined ourselves, right? That's pretty cool, I think. So we see that we don't like do-nothings, right? So let's go to the error here. And if we would then remove this line, then indeed we would get rid of the warning. So that is, I think, a pretty cool way of dealing with technical debt and with your own patterns and with your own best practices in Java code. So what kind of bug checks do we have at Picnic? Because we have quite a few custom bug checks as well. There's a few categories. So on the one hand, we have checks that are helping our developers write correct code and use APIs correctly. So for example, we want our code to not just fall back on the default time zones and on using local date time now, for example. Thank you. So we have bug checks that actually flag these kind of usages and that force you to think about what is the actual time zone that I'm going to use here towards my customer, towards my system. And if I want to have the current time, then I need to somehow obtain and via Spring inject a clock and get the time from that so that we can also easily mock it and replace it in testing, for example. So this is one where it's fairly easy for us to find good patterns. And of course, these are all patterns that have arisen through many discussions, usually on PRs, etc., that we can now encode into such a bug check. The other category is where we want to avoid some runtime errors, right? Because even though you invoke something, it doesn't mean it's going to, if it compiles, it doesn't mean it's going to work at runtime. So an example here is when working with SLF4J. Some people can't forget that SLF4J uses the curly braces as placeholders rather than the %s, which is in the Java string formatting as a sort of as a placeholder. So we wrote a check that actually looks at the string and sees if somebody actually accidentally used the %s. And they say, well, that looks nice, but you probably meant to say curly braces here rather than a %s as a placeholder. Or if you have the info statement here, you have two placeholders in the string, but you only provide one argument to the login statement. Again, it's not easy, but it's possible to write a bug check to flag this and to inspect all of the invocations of the logger, where you look and parse the log string at compile time in this error-prone check, and then see if the arity, if the number of arguments is actually corresponding to what was defined in the string. Another category of things that you can enforce and that you can check using these custom bug checks is more along the lines of style, code style. So, for example, if you have annotations and you have something like order and then value is 1, you can much more tersely write this as order and 1, because value is the implied parameter here, and the implied targets for a single argument to an annotation. Also, if you have an annotation, you can have an array of values usually. But if it just has a single element and it has a trailing comma here, which is also valid syntax, but we don't really like that, then we can create a bug check, and it actually can flag this for you, but it can also rewrite the code, as we saw, to actually make it uniform and make it, yeah, in my opinion, also nicer. So there's correctness, there's avoiding runtime errors, there's the style issue. There's a lot of flexibility in here. And that's also a little bit of an issue, right? Because if I just showed the headers of the checks, right? I didn't show the implementation of these checks. And some of them can be pretty intricate. I mean, you have to know your way around in Java as abstract syntax trees. And you have to work with this error-prone API, which is very powerful, but also, well, I would say it does have a learning curve. So it's not for everyone. It's definitely not trivial to write some of these checks. It's worth it, at least for us at our scale, but it's not easy. Especially if you want to also emit these really good suggestions and replacements, because you also need to take care of that if you want to make your check maximally useful. So given that, you might be thinking, but actually what is happening here is that we're sort of rewriting code, right? So wouldn't it be really nice if you could have some work by example kind of approach, where you say, okay, I have a little bit of a bad example here on the left-hand side. For example, if you say a string equals an empty string, it works, it compiles, but it's much more intention revealing if you would write this as a string is empty. What if you could take this sort of approach and not fiddle with abstract syntax trees, etc., and just have some magic in there that does this for us? And that is actually also possible. And that magic is called Refaster. So with Refaster, what we can do is we can actually specify some before code, so an example of the code that we want to match, that we want to replace, that we want to rewrite, and some after code. And then Refaster and, in the end, error-prone take care of all the nitty-gritty details of actually finding the matches for this kind of code and doing the rewriting and just working as a large-scale refactoring tool. And the way you do this is by creating a class that contains some methods, at least one with a add before template annotation, where you have the code and the thing that you want to match, and one after template annotation, which shows how it should be. And I'm going to show this as a demo to you as well. For that, we have a third Maven project called My Refaster Template, where we're going to have such a class, and we're going to compile this class with the Java compiler with an additional different annotation processor, the Refaster resource compiler. And this will result both in a Java class file output, which we're going to ignore, because this code is never going to run. It's just there to inform Refaster of how you want code to be rewritten. And that is encoded into a Refaster file. So you will see that we'll also get this empty string.refaster file out of it. And once we have that, we can configure error-prone to pick up this rewriting template, this empty string.refaster file, and to actually apply it to our code, to our buggy app. So let's do that. Let's have a look at how we can do that in practice. And again, the goal here is to replace this equals with is empty in this case. So what we have here is this class that I talked about with actually two before template methods, where we can see that we are targeting rewriting expressions of type Boolean. We can see that here in the return type. But not just any expression of Boolean type, but in this case, if it has the form of some expression of a string and then a method call to equals with a literal empty string in there. That is what we want to match. Or, alternatively, you have other creative people who say, no, let's call length on string and see if it's 0. So both of these cases we want to turn into the string is empty. So this string, this name here is just a placeholder. It's not really important. The name of the method here is also not really important. This is sort of the free variable that we have in our rewriting. It doesn't really matter what is here as long as it is an expression of type string. And if we go back to our application, it's actually an array dereference that we have here that will result in a string and that we want to rewrite then this part. So that is all pretty flexible. So what we still need here is an after template. So let's put this in there, empty string, there we go. So we want to have here an after template. And by the way, we also want to match negations. So if we say not, then we also want to rewrite that. That's a little trick that we have here. And we rewrite it to, well, again, something that returns a Boolean expression, because again, we need to rewrite to something that still compiles. But instead of invoking length equals 0 or equals empty string, we are going to invoke is empty on this. So that's all that we need to do to make this check reality. Now, I'm going to show you here in the configuration of our POM file that we are again running the compiler with a plugin, but a different one. This is called the Refaster rule compiler. And we pointed to an output file. In this case, one level up, I'm going to output the empty string.refaster file, which then we can use in our buggy app to actually do the checking and the rewriting. So let's run this. Clean verify. There we go. Let's just check that we have the file. Yeah, that's all good. Then I'm going to go back to my buggy app application, and I'm going here to error prone, and I'm going to configure it with EP Refaster. There we go. Again, using the EP patch checks flag, but now not referring to the built-in checks or any of the checks that we add to the class path ourselves, but we're going to refer to a Refaster file, and this is the file that we just created by running this Refaster resource compiler on the template that we have. And we're going to patch this in place. So let's run this. Maybe clean verify. Let's go back to our source code. And ta-da! We have is empty. How cool is that, right? So we had some before code. Just to reiterate, we had some pretty easy to write before templates. We had a pretty easy to write after template. And all the machinery around that was handled for us by Refaster and by Error Pro. So we actually can get automated refactoring at scale going this way. Now, can it only do this expression rewriting? No, there's also an option to do actual blocks of statements and to write particular sequences of statements to other sequences of statements. Like if you have this manual swapping code, you can rewrite it to a single collections.swap method. That's pretty cool. But I think it's also really nice to look at some examples of how we use Refaster. For example, when we migrated to Java 11, when it was released, there's some pretty nice improvements in the API there. And you can teach people to use those, and you can do the bushcart rule. So for new code, you can use it. For old code, maybe if you touch it. But how cool is it if you can upgrade all these 4 million lines of code that I talked about in one go to go from the old API to the new API? So we did this, for example, with a simple rewrite on optional, where you used to do not optional is present. And then in Java 11, we finally got optional is empty, which reads much nicer. So again, create a Refaster rule, compile it, hook it into your error prone, and you actually get this rewriting for free on your whole code base. Pretty nice. There's some other ones in the JDK migration as well, where we used to do this on a stream. You would first maybe filter on optionals in the stream if they were present, and then map optional.get over all these optionals that had a value. Or if you were using Guava, you might have used stream.flatmap and then the streams stream method. We do use Guava, and this is also a nice example of showing where a rule matches both JDK APIs but also Guava APIs. But we wanted to rewrite those to standard Java stream.flatmap and then optional stream method, which that's the new method that came in JDK 11. So again, And this is super powerful to be able to migrate your whole code base in one go from an older version of Java to a newer version of Java, and also improve all the code that is in there by doing these kind of rewrite actions. We don't do this just for core Java. We also use, for example, Reactor as a library, as a reactive library. Again, doesn't matter really what the exact details are. You don't have to know the API, but we have the ability now to spot some anti-patterns when we see in pull requests people using it slightly in the wrong way. Encode this into a Refaster template, hook it into our builds, and make sure that it never occurs again in any of our code. So there's some more options here as well that we have for Reactor rewriting. Also, the Refaster any of allows you to match any of some of the options. I skipped over that a bit in the previous one. What is also interesting about this example is that in the after template, we're actually calling a static method to optional. If you would just plainly put that into the source file, then it might be that it is not imported, right? So you can also use an import policy in the rewriting, saying, okay, if we're going to replace this kind of code, also add a static import for this to optional method. These kind of things are all possible and tweakable using Refaster rules as well. So one way you use this, if you want to use an API which uses a certain method to another one, and that might have a fluent list of invocations, such as the examples that we saw, then Refaster is really, really easy to use. Or if you have these blocks of statements that you want to rewrite to another block or to a single statement, that is also pretty well possible using Refaster. However, it does have some limitations, right? So what we saw is that Refaster is really about rewriting expressions. It's really easy to do it, right? You just have to define some before and some after code. But there's limited expressiveness, and Refaster is really about rewriting code. It's not about spotting anti-patterns and giving good error messages about that, like we saw with the BugChecks. So there's a place for both. There's a place for the BugChecks, there's a place for Refaster rules. Because BugChecks allow you to do much more intricate manipulation of these abstract syntax trees. And you have the full ASD available, so you can do much more powerful things, but you need to write more code in these BugChecks to do so. So if you want to create a BugCheck yourself, this is actually coming from the error-prone site itself, ask yourself a few questions. Is this actually a bug that's easily understandable? Can I explain this in a short compiler error message? And also, is it easily fixable, right? If you have to go through 12 steps and a lot of hassle to actually fix it, it might not be something that you want to add to your generic build pipeline. So these are kind of concerns that you would have to take into account if you're going to adopt a tool like this, and if you're going to create your own BugChecks, and maybe even contribute BugChecks to error-prone itself, which is also a possibility. So what I say is the bottom line is that when a user sees one of our or your errors, they should think, I'm glad error-prone caught that for me. That's sort of the sentiment that you need to strive for here. You might also be wondering, okay, that's all great, but you showed some demos, but how does it actually fit into your CI pipeline at Picnic, and then how is this actually applied? And the idea is actually pretty simple. So every time you create a pull request, every time we do a build, we will run all these Refaster rules and these error-prone checks in patch mode. And if there is a difference, so if there's a non-empty git diff, well, then there's something that you missed, right? And then we can give a nice comment on the pull request. Says, okay, maybe you forgot to run the patch checks, and please run the scripts. There are some style errors. So this way, you will not be able to merge your pull request unless you addressed all of these Refaster and BugChecks that we have. And that is our custom checks, but also the stock checks that we have enabled, and the Refaster rules that we have devised for, well, with the examples that I've shown before. But it doesn't end there, because we are so excited about error-prone that we also are actually investing in this. And we have Stefan Schroevers, also Rick Ossendrijven, who's also here right now, who did some research into extending the capabilities of error-prone, and Refaster in particular, because as I've shown, it's really cool, it's really nice to be able to write this, but it's still somewhat limited. And we have a very concrete use case. We wanted to be able to rewrite our code from old RxJava to the new Reactor library that we have. And you can get pretty far with Refaster as it is. But at some point, you have methods with a return type that is of a RxJava type that you would want to migrate to a Reactor type. And as you saw, you can only rewrite expressions. You cannot rewrite method return types. So Rick and Stefan looked into this and extended actually Refaster and Error-Prone to be able to do this, which I think is really cool. Also led to a paper submission at a conference. So yeah, we're really excited about this because it works, it's cool technology, and it's actually useful in every Java project that we have. So I would urge you to go practice the new superpower, right? I think we've all seen some pretty cool stuff here. So first of all, just go to the Error-Prone site, browse a bit around. Also, I must warn you, we do have a fork of Error-Prone that we run. We also have contributed a lot of patches to Error-Prone, and some of them have been merged, some not. So if you really are going to use this, also look at this fork, and we've made some incremental improvements around the ability to emit multiple Refaster files and use them in one go, and all kinds of convenience things that help us, and that might also help you. We also, I think it should be only fair to shout out to Stefan Schroevers, who's our resident Error-Prone expert. I think it's really a testament to what a great engineer can do for a whole tech team. So if you have any in-depth questions, do reach out to Stefan. I think with that, we come to a close. Thank you so much for being here. I hope you can tell that I'm really excited about this. I hope you are too. If you would like to work with this kind of stuff, please visit our booth and please go to this Join the Picnic website, because the 180 engineers that I mentioned in the beginning, it's only the start. We have so much scaling to do, and I would love to work with you. I would love to have you on our platform team also working on this kind of tooling, or in other teams using Java 17, using all this cutting-edge technology to build the best milkman on earth. So again, thanks a lot for being here. I hope you enjoyed it. If you have any questions, feel free to come up after, because we're a little bit out of time here. Also, feel free to reach out to me at the booth. And thanks, everyone.